Okay. I'm going to talk about space trusses relatively briefly. Basic idea. This is really considering truss structures in three dimensions. Okay. So this is the basic idea. What you have is a structure that has the connecting where it connects together, or the supports that are provided are through ball and sockets. And as we're looking at it, so tetrahedron is the simplest form of this. Okay. And it's formed by six members being interconnected. Right. Now, what we need to do for the design is we're going to treat these as two force members, except in three dimensions. So you mean like you have a force this way and equal opposite force in the other direction, acting at the other connection point, the other ball and socket. So when we see a ball and socket um, connection, what that really means to us is that there's no reactive moment about this point. Okay. So anywhere these connection points. So the only thing we could do is come up with a set of equations that would represent this. If we're doing method of joints, we'd come up with a set of equations that only say the summation of the forces are equal to zero in the three directions. Okay. We can also do a method of sections with this, but that requires that we cut this at a certain point. Okay. And then we can do, we can do the summation of the moments and make those equal to zero also. Okay. All right. And just procedure for analysis. And this is just the one page. There's really just a short part on this before we can look at an example. So here we go. Method of joints. And here you apply these three equilibrium equations. Okay. So when you're solving a structure, a space truss structure problem, you still follow the same general approach as we did in two dimensions, because this is really essentially the same problem except of a truss structure, except in three dimensions. So you could actually go through and find the reaction. So you can come up with solving the entire structure, find the reactions at the points where it's actually connected externally. And from that, you can use that to go through and apply the method of joints like we did previously. Okay. All right. And the second part, you can actually do a method of sections. And same idea, you can actually cut through certain members, right? If those are the forces that you care about. Now when you do this, now you have the possibility of six equilibrium equations, right? These are all you could say, the forces, summation of the forces in the x direction, y direction, and z direction all must be equal to zero. And the moments about each of these axes must also be zero. And this represents, of course, any point on the structure. Cannot be any rotation on the structure. So this has to be true. Okay. And this is also for like any point on the structure also. All right. Otherwise, it wouldn't be in equilibrium. Okay. Just one more for you here. Uh, there's an interesting. Here was a story of the Hartford Civic Center. I do remember this. And this is back in 1978. This was a space truss structure that they used, and it. Not to say that a space truss structure is bad, but there were other issues that came about. But it was rebuilt, of course, afterwards. But in 1978, it collapsed, and it had been snowing, and I think it rained that night. And because of all the weight, it caused it to collapse at that point. According to the design, or at least after the investigation, it said it had begun to fail even before that. Okay, so just because of design flaws, the analysis was not correct. So it basically put it over the edge at that point. Fortunately, nobody was there at that time, although they did have a game earlier in the evening. So, but there's an example, and you know, hopefully you don't want to be if you're a structural engineer, you don't want to be associated with a project like this, right? Okay. So that really is all there is. So what is it? Essentially, space trusses are just extending, a truss structure in three dimensions, right? So with this type of tetrahedron design to it, Okay, essentially. All right. So we'll take a look at some examples, but that's really about all it is, and it's really a matter of taking a look at and solving problems. And you can imagine, of course, that the problems can be significantly more complicated pretty quickly with that, just in with this additional dimension. Now, before we had two equations for method of joints. Now we have potentially three. And method of sections, we had three equations. Now with three dimensions, we have six. Okay, so that's about it for that.